right, everyone, welcome to class. Happy Friday to one and all. Today is April 9th. Right, so we're starting chapter 17. This is our second to last chapter. Let me make a couple of comments regarding the test. A lot of people couldn't upload the written problem set because I was just grading it before class, and Canvas was saying it's a media presentation, or it's this or it's that. So if you want to turn in your written portion of the exam at the problem set, I'll accept it and I'll grade it. Okay, so you guys didn't do anything wrong. You uploaded it, but when I went to grade it, it's saying it couldn't open. So those of you that are here, or those of you that are listening, please upload the written portion of the exam if you had some issues. You can also hand it in to me, and I'll grade it by hand. Okay? And I think the scores are very good. So everyone did fine on the exam, those that did it. Some people still did not take the exam or turn anything in, but that's fine. And I know you'll turn it in when you're ready. So I wasn't talking about you. All right, a couple of things here. Let's start working on quiz 4. Okay, that's going to be due April 26th. And test 4 will be on April 26th. Right, there's a lab. First of all, two things with regards to the lab. One is upload the problem set. That was last week's lab. I think if you did the problem set, maybe the test would have been a little bit more easier for you. But if not, that's okay. Work with your groups and upload that to Canvas, and I'll put in points. There's a lab this Friday, right after class, on spontaneity. This is our last lab. So join us for this lab today or next Friday. And I just made some notes with regards to the lab because it's material that I have not covered. So these notes should help you. And also I made a video that should help you with this lab. It's a very short lab, and you'll end up with your last Chem 2 lab being a very short lab on spontaneity. Okay, this has to do with thermodynamics, the topic of chapter 17, this chapter. Work on homework 17, and I'll give you a due date. Okay, so work on that, and I'll put in the 10 points. And then for your lab, since we're heading towards the end, update your lab notebook, and I'll give you 100 points. And for those of you that are doing the clutch prep online tutoring to help you with this course, continue to do that at the end of the term. I'll look at the computer. I'll look at the computer. Whoever did everything, I'll give some points towards your final grade. Not a lot of points, but it may make a difference between an A- and an A, or one of those things, B+ and an A-. And do come to lab also. So I decided that if you have come to all the labs in person with myself and Larissa, I'll also give you some extra credit points towards the lab. All right, so that's if you've come. So if you've already come to all the labs, come to this final lab, and for doing the right thing, I'll give you some points. Okay. And anything else you guys can think of? I was going to make a final exam. I have not made the final exam, but
is it still like the online, or is it in person?
Yeah, it's if I do make one, it's going to be just for my assessment. So that you do an evaluation for the class, but you also do an evaluation as the final exam. So it's not going to hurt you. Okay, so yeah. the final exam that I'm going to make is multiple choice questions, and it's cumulative, but it's not going to affect your grade. If you score higher than any of the 4 exams, I'll replace it. If you don't score higher, I just throw it out. Okay? So that's your final exam. Yep. I have not made it, but it'll be like 25 or 30 multiple choice questions. It's used mostly for my evaluation. They use it, my bosses, and it won't hurt you. Okay, it won't hurt you. We do ask you to take it, and I don't know when the date is. I'm just focused on Test 4. Yeah. Test 4 actually covers Chapter 17 and 18, and that's not cumulative. Okay, so and that's April 26th. Are any other questions or comments? Yeah.
Is it okay if we upload the problem set next week?
Yes, you can upload it next week. Yeah. Yeah. All right, so start working on your homeworks. Let me go over Chapter 17 with you guys. Chapter 17 has to do with thermodynamics. All right, so there's 3 main terms of thermodynamics. By the way, what do you think thermodynamics means? Well, I don't have... I'm sorry, say it again.
I said thermo is heat.
Thermo is heat, correct. Very good. So anything that has to do with energy. Okay, energy. Maybe I'll say energy exchange. Okay. All right, so very good answer by Adriana. Thermo is heat, but really when we talk about heat, I want you to think of delta H, which stands for enthalpy. Actually change in enthalpy. And I don't know if you remember this from Chem 1, but if that value is negative number, we call that an exothermic reaction. And if your delta H enthalpy is positive, we call that an endothermic reaction. Endo means requires heat. Exo means it takes heat to the outside. The reaction gives off heat. Exo means outside. Endothermic reaction. So you're right, Adriana. Thermo does have to do with heat, but really what you are referring to is delta H. Okay, there's other types of energies that's not just heat. Okay, there's another type of energy, and this is the new part of this chapter, and this is called entropy. Okay, entropy. One thing I want you to know that S can be standalone, or it could be change in entropy. If it's a change in entropy, then it's delta S. So delta H, change in enthalpy, delta S, change in entropy, and then S is entropy by itself. So S can be standalone. Okay, so how do I define entropy? Let's see here. How should I define it? You guys live in a dorm or live in an apartment? Where do you live in? The dorm, okay. Or even in my home. Here's a kitchen sink. Okay. This is not the best example, but okay, close your eyes and imagine your kitchen sink. It's nice and clean, okay? A sink. Okay. What do you think is going to happen? You guys live in a dorm or an apartment, okay? What do you think is going to happen to that sink after 2 weeks? Tell me, there's no wrong answer.
It's going to get dirty.
Correct. Plates everywhere, spoons everywhere.
Bacteria is going to accumulate.
Bacteria is going to accumulate. The bacteria. What else? Mold.
It's gonna smell. Yeah.
It's going to smell. Okay. Yeah. So what just happened just 2 weeks ago was a nice and clean sink. I spent hours cleaning the sink and scrubbing it all just after 2 weeks. Okay. So I would imagine students like you guys know very much about entropy. Entropy means disorder. Okay. Entropy means a disorder. So the best example would be someone's bedroom, the dorm room, the kitchen sink at the dorm or in someone's house. See, you clean all the dishes, and then after a week, everybody says this, 2 weeks, a month, it's going to get disordered, okay? And entropy is really just a measurement of disorder, okay? One way we can also say disorder is spontaneous. Okay, so this just seems to happen spontaneously. You really have to put work. You really have to put work to make your kitchen sink clean. If you don't do work, this just seems to be a spontaneous process, isn't it? Right? You know how just dishes and spoons and all sorts of stuff accumulate. It seems to happen spontaneously. Okay. So we tend to say that this. I'm not talking about a reaction here. I'm just talking about life, or the kitchen sink. We have here this process is an increase in entropy, or I'll just say increase in S. Okay, S stands for entropy. So entropy really just means, in this context, disorder. Okay, disorder. Like enthalpy before us, entropy is related to the signage. Okay, the sign. So if your entropy is positive, okay, then we have what's called a spontaneous process. I would call this positive entropy, right? Okay. So if the value, we have to assign numbers to these things. If the value is positive, then that process, I'm using the word process here, not reaction. I'm using the word process. The process is spontaneous. Okay. If that number for S or delta S is negative, then it would be the opposite of spontaneous, which is non-spontaneous. So let me throw at you some examples here. Okay, let's say we have a solid going to a liquid. Okay, how about like ice? Okay, ice, which is just water. It goes to a liquid. All right. What do you think the S is? I'll just use change in entropy, S. Do you think it would be positive or negative? Solid. You imagine a block of ice here. Okay. What would happen over time? Melt. So do you think that process is spontaneous? Would this be positive or negative? Okay, this would actually be positive. Okay. Positive. I'm talking about entropy delta S. Okay, how are the atoms arranged in a solid? Aren't they like this? Packed is right. How are the atoms, the molecules, the atoms arranged in a liquid? Okay, not so packed, loose. So yes. Okay, this would be a positive entropy. Okay, solid going to a liquid. How about a liquid going to a gas? It's going to be still positive. Very good. Okay, a gas would be even more, as Joshua said, loose. Well, a gas is even more loose if you're talking about the molecules. Okay, very, very loose. So, entropy, I want you to remember more disorder. more disorder. More space. Okay, gas takes up a lot of space. Big gas around, it takes up whatever it can. More space. You here have this takes up a lot of space. Even more mass. What else? More mass, more motion. Molecules move. Okay, so if you ever study structural biology, you'll realize that molecules are actually moving. The molecules rotate, bonds rotate. Molecules really have a lot of motion to them. So more motion. All of these are usually associated with an increase in entropy, more disorder. So just remember, heat, as Adriana said at the very beginning of this class, is an energy, but this is also an energy. Okay, this is also an energy. In fact, the whole concept of thermodynamics has to do with energy. Okay. All right. How about this? If you have a gas and it goes to a liquid, would that delta S be positive or negative? Are we going to more order or less order? Gas to liquid? It should be negative because, there's more order. Okay, more order. Molecules are more, packed. Molecules have more structure to them. Okay. And what do you think is the most ordered substance of all time? This is trivia, not chemistry. But what is the most ordered substance? Anybody want to take a guess? The most ordered substance would be a crystal. Okay, a crystal. Okay, a perfect crystal, because some crystals are not very ordered. There's a little disorder. The packing of a crystal may not be so perfect, but the most ordered substance would be a crystal. Okay, every molecule is packed. Every molecule is standing still. Every atom of that crystal, I'm talking about a perfect crystal. It's just perfect. There's no motion. There's no movement. Nothing. So, a lot of order here. All right, everyone, we talked about delta H very briefly. I just introduced entropy. With entropy, I want you to think of the word disorder. This really doesn't tell us if a reaction is thumbs up or thumbs down. When I say thumbs up, the reaction is going to go to products. If the reaction doesn't go to products, thumbs down. What really decides is this term here, delta G. Okay, delta G. So delta G here is Gibbs free energy. This is the final in our Gibbs free energy. All right, so delta G is Gibbs free energy. This is the final judge of whether a reaction is going to move towards products or not. It's the final arbiter. It's the final judge. And that's called Gibbs free energy. Okay. So it's the judge. And if your delta G is negative, we call that an exergonic reaction. This is a reaction that's going to move to the products. Okay. Period, paragraph. Okay. And if your delta G is positive, it's an endergonic reaction. This is a reaction that's not going to go to the product side. Period, paragraph. So an exergonic reaction is a reaction that favors, a reaction will go to products. If it's endergonic, the reaction will not go to products. Will not go to products. So we'll put a big red X here. Well, I want you guys to look at this equation here. You see, in order for a reaction to go to products or not, from a thermodynamic standpoint, this delta G is going to take an input. Okay, what will it take input of? Delta H, and it will also take input of delta S. And what else can determine whether a reaction will go in the product side? Temperature. Some reactions, if you increase the temperature, you see it will move to the product side. Some reactions, if you lower the temperature, it will go to the product side. So let me just make this triangle here. Where should I make it? Okay, I'll just make it here. I'll just make it on the next page here. So let me make this triangle. So we see we have the final judge delta G, and that's going to take feedback from delta H. So we learned this in Chem 1, delta H and LP, heat flow. And it's going to also take input from delta S, which is entropy. Sometimes you'll see S can also be just plain old S. Okay. All right, and delta H and delta S kind of influence a reaction, whether it's going to move forward. Is the reaction going to release heat? Yes or no. Is the reaction moving towards order or disorder? Yes or no. And then at the center of this is temperature. Okay. And again, the final equation is delta G equals delta H minus T delta S. Again, if delta G is minus, we call that exergonic. The reaction is going to move to the products. If it's positive, it's endergonic. If delta S is positive, it just means the reaction moves towards more disorder. More disorder in the product side. If it's negative, then it's more order in the product side. If your delta H is positive, that's an exothermic reaction, exothermic, and that means heat is released. Heat Q is if it's positive. If delta H is positive, this is endothermic. That means heat is usually required. And if your delta H is minus, that means heat is released. And we call that an exothermic reaction. If I remember, it's delta G, Gibbs free energy, that determines whether the reaction is going to move forward or not. Okay, let me define Gibbs free energy for you guys. Okay, you may see this when you take your MCAT or any of the other exams. Gibbs free energy. Delta G stands for Gibbs free energy. I guess the guy who discovered this, his name is Gibbs. And this is energy that's available to do work. Okay, energy that is available to do work. Energy that is available to do work. Energy available to do work. I'll put work in capital letters. Work. So what do I mean by work? This is real energy. Okay, energy that can be harnessed. Okay, work is energy that can be harnessed. Heat, you see, cannot be harnessed. Heat just goes away. Okay, try heating a pot of water, and it's really hot, and like, oh wow, if I could capture that to drive my car or fuel my battery. It's really hard to harness heat. Work is energy that can be utilized. For example, I don't know, the biology people know this. If you're not a biology major, this may maybe a little different, but that's okay. I'm not going to test you on this. But ATP is a molecule that does work. If you break apart that ATP molecule, release a phosphate, it releases about 33 or so kilojoules of energy. And where does that energy go? It's used to do work. Okay, move a cell. All the little cilia, those little small hairs, it helps them propel. Okay, all those things. Okay, make another reaction. That's endergonic, makes it exergonic. Okay, that's what we mean by work. Okay, energy that could really be captured to do something else. So Gibbs free energy is energy available to do work. Another thing I want to mention here, we have delta G equals delta H minus T delta S. There's another version of this, and it's delta G naught equals delta H naught minus T delta S naught. Okay, this little superscript, that superscript with that little O, that means naught. Delta G naught equals delta H naught minus T delta S naught. Okay, so this naught means standard state. Standard state conditions. A lot of people miss this based on my experience. Standard state conditions is a very specific set of conditions for the reaction. And those conditions are, if there's a gas anywhere in the reaction, the gas must be at 1 atmosphere. If you're dealing with a solution, remember a solution is solute plus solvent. If you're dealing with a solution, that solution must have a concentration of 1 molar. And the temperature of the reaction is at 25 degrees C. Okay, these are called standard state conditions. And if you're measuring delta G at these conditions, or if you're measuring delta H of a reaction under these conditions, or if you're measuring delta S of a reaction under these conditions, the temperature here is 25 degrees. If you're measuring it under any of these conditions at this temperature, that's standard state. Okay. So that's called delta G naught, delta H naught, delta S naught. We look at these values at the back of the book or some internet source. Okay. So this equation is not the same as this equation. Okay, so you see this is at any other temperature, any other pressure, if you're talking about a gas, any other temperature. The minute you talk about 1 molar solution, the minute you talk about 1 atmosphere gas, the minute you talk about 25 degrees C, the minute you put all these things in, you're talking about standard state. And there's a book, the back of your book, in fact, any textbook, you can look up all these values. Okay? So a lot of students miss this with this. This is very specific temperature and pressure. This is not any other temperature and pressure. All right, let me just go back to the very first page of our notes here. I just want to tell you something. I got here, just very quickly here, I got here 4 reactions. All right, so notice here the arrows are all going in one direction. Okay, so arrows are all going in one direction, which means there's no equilibrium. And look at the delta H here, okay? And by the way, how is this measured? Is it measured in standard state? Yes, it is. It's measured at standard state, delta H naught. But look at the numbers. Okay, negative, that means it's exothermic. Negative, that means it's exothermic. This third reaction is positive, right? It's positive. That means it's endothermic. And this reaction here, positive 25 kilojoules per mole, is endothermic. Okay. So here we have the first two reaction exothermic. You guys agree? It's a negative. Reaction 3 and reaction 4 is endothermic. You guys agree? It's positive value. So this would be an endothermic reaction. This would be an endothermic reaction. Looking at delta H now, this would be an exothermic reaction. This would be an exothermic reaction. Now let's talk about delta S here. Let's put delta S in blue. Okay, we already got our delta H values, okay, given to us in the table. But what about the delta S values? All right, so watch with me here. So what would the delta S for this reaction be? Okay, so here we have 1, 2, okay. We got 3 moles of a gas. Okay. And here we got a gas and 2 moles of a liquid. Okay, 3 moles of gas, 1 mole of gas, 2 moles of liquid. So this may be kind of hard to recognize, but this is what's called a combustion reaction, the very first reaction. And combustion reactions usually lead to more disorder. So you'll just have to take my word on it. The delta S for a combustion reaction is going to be positive. Here you got 3 moles of a gas going to 1 mole of a gas and 2 moles of a liquid. It actually leads to more disorder because it's a combustion reaction. Right, how about this reaction here? Aqueous and aqueous, dissolved in water, dissolved in water. It just goes to water, okay, liquid water. So this is H plus in water, so that's some disorder. This is H plus, this is OH minus in water, so that's some disorder. Here this is just pure water without any H plus, without any OH minus. So this is going to be negative. Okay, so pure liquid, this is H plus and water, more disorder. OH minus and water, more disorder. Let me go back, and I'm not going to test you on this, but I'm going to change this delta S to minus. Okay, you see here I got 3 moles of a gas, and again, if I confused you, don't worry about it. 3 moles of a gas. Here I got 1 mole of a gas plus 2 moles of a liquid. So 3 moles of a gas is more disorder than 2 moles of a liquid and 1 mole of a gas. So I'm going to change this to minus. Okay, you're making a liquid which is more ordered than a gas. Okay, so don't worry if I messed you up, but I'm going to change that to minus. This is minus because this is pure water. And what are our reactants? Our reactants are H plus and water, more disorder. Our reactant is OH minus and water, in water, more disorder. All right, so I'm going to call that minus for the second reaction. We're talking about delta S to change in entropy here. All right, what about this one? Here I expect everyone to know this. A solid going to a liquid. Will our delta S be positive or negative? Positive. Okay, so this is something I would want you guys to know for any exam. And this is something I would want you guys to know for an exam. you have a solid, very ordered, and it's going to something dissolved in water and another thing dissolved in water, aqueous and inaqueous. Is that more disorder or less disorder? More. So our delta S will be positive. Okay, more disorder, it's positive. So hopefully reaction 3, reaction 4, you'll recognize that it's going to be more positive. All right, what's the point of all of this? The point of all of this is that it doesn't matter your delta H. Okay, it doesn't matter your delta H. Your delta H and your delta S are independent of one another. Okay, that's what. Does a decrease in enthalpy mean a reaction proceeds spontaneously? The answer is no. Okay, so you have to measure these independently. You can have something that's exothermic and be a positive delta S. You can have something that's exothermic and be a negative delta S. You can have something that's endothermic and be negative. Okay, so they're all one or the other. They're all independent of each other. Okay, so that's the point of this. Let me just read this to you guys out. Just because a reaction is exothermic does not mean it's spontaneous. Exothermic meaning delta H is negative. And just because a reaction is endothermic, delta H is positive, does not mean it is spontaneous or non-spontaneous. Okay, that's the take-home point of all of this. Okay, that's the take-home point. All right, so the last 10 minutes or so of class, I just want you guys to recognize this here. Gas is going to be the most disordered. Liquid would be second most disordered, and then solid, with the atoms all packed together so nicely, will be the most order. Okay, and entropy is order. Okay, order. So that's the order in which we're going. And you can actually see this here. Okay, look at the way the atoms are. Here the atoms are ordered. And here the atoms are a little bit less ordered. Okay, less order. Let me go over this here kind of quickly here. All right, so here's the equation that I'd like for you guys to know. All right, and don't forget we have a version that's in standard state as well.
What page is on those?
These are in our notes that I handed out.
Oh, the lab.
Yeah, the lab notes. Yeah, I'm kind of taking a quick detour here, but I'll get back to our lecture notes here. Right, so remember here, delta G, if delta G is negative, that means the reaction is a go. That means the reaction is going to go towards the product side, correct? All right. So that's what we want, if you want a reaction to go towards the product side. Okay. If delta H is negative, what does that mean? It means heat is released. Usually if heat is released, what does that mean? Exothermic usually means the reaction is going to move towards the product side. Doesn't mean it will, but it's enthalpically favored. How about we put it that way? Enthalpically favored. What happens if your delta S is positive? More disorder, is it not? More disorder. So I'm going to call that entropically favored. Okay, you know, things kind of want to tend towards disorder, like your kitchen sink. just happens by itself. It's going to get dirty, or your room just happens by itself. So this would be what I'll call entropically favored. Okay. So let's look at this table here. So if your delta H is negative, that's enthalpically favored. If your delta S is positive, that's entropically favored. You will always have a delta G negative. Okay. So just put here a negative sign and a positive sign. So negative with a positive, positive into negative is negative. So negative and negative is negative. It's always going to be negative. All right. So under any temperature, your delta G will always be exergonic. So here's a reaction that's entropically favored and enthalpically favored. Okay, everyone see that? All right, let's do the opposite here. Let's see our delta G is going to be positive. If our delta G is positive, that's called an endergonic reaction that's not a go, no go. What if your delta H is positive? Okay, we call that an endergonic reaction, so I'm going to call that enthalpically disfavored. It requires heat. Anything that requires heat or anything that requires anything probably means the reaction is not going to happen, okay, by itself. So if our delta H is positive, I'm going to call that enthalpically disfavored, right? If your delta S here, I'm talking about delta S now, if your delta S is negative, that means it's tending towards order. That means, yeah, you got to go in there and clean your dirty kitchen sink. Okay, you got to put in work. So I'm going to say you're working towards order, cleaning your room, cleaning your kitchen sink. So I'm going to say if your delta S is negative, you're entropically disfavored. All right. So let's look at our table here. If your delta H is negative, I'll put this in a red square. Actually, let's skip that here. Let's go here. If your delta H is positive, okay, that means you're not entropically favored. If your delta S is negative, that means you're entropically not favored. You will always be positive in terms of your delta G. Imagine here a delta H that's positive. Imagine here a delta S that's negative. Negative into a negative is positive. Positive and positive is positive. So you'll always be positive regardless of your temperature. If your delta G is always positive, then you're non-spontaneous. Okay? Right, now these last two things are where it gets a little tricky. And then let's use our last 4 minutes to discuss this. All right, think with me now here. If your delta H is negative, okay, imagine put a big minus sign there, okay? But your delta S is also negative. Okay, so negative delta H means it's enthalpically favored. Okay, but a negative delta S, you have to be with me here, it's entropically not favored. So this is favored delta H wise. It's disfavored delta S wise. So who's going to win? Okay, that's where temperature comes into play. Okay, these last two scenarios are where temperature comes to play. So I want to tell you guys that here delta H negative means delta H favored. Delta S negative meaning It's not favored in terms of entropy, so this is favored from the thermodynamic perspective of delta H. This is disfavored from the thermodynamic perspective of delta S. So this is where you have to put in temperature. So it turns out that it's negative at very low temperature. Okay? So if this is negative and this is negative, okay, to keep this as negative, you need a low temperature as possible. Okay? Now, if this is negative and this is also negative, if your temperature is very high, it makes this very positive. Okay? So it's positive at high temperature. So at high temperature, it's not going to favor products, but at a low temperature, at a low enough temperature, it's going to keep this negative, the delta G negative, and so it's spontaneous at low temperatures. All right, our final thing here. If your delta H is positive, okay, remember, if your delta H is positive, that means it's an endothermic reaction. It's not favored from the thermodynamic perspective of delta H. If your delta S is positive, are you favored? Yes. Okay, if your delta S is positive, you're moving towards more disorder. So again, this last scenario is who's going to win. You have a reaction that's not favored in terms of delta H, but is favored in terms of delta S. Okay, now you have to look at temperature. Well, it turns out that this is positive at very low temperature. Okay. So if your delta H is positive, your delta S is positive. Okay. To keep this temperature very low makes this whole thing positive, so it's going to be non-spontaneous at low temperature. Okay, everyone see that? If your delta H is positive, not favored. If your delta S is positive, okay, if you have this temperature very high, it makes this whole thing negative. So it's going to be spontaneous at high temperature. Okay, at a very high temperature, this positive will make this whole overall thing more and more negative. If this is more and more negative, your delta G will be more and more negative. Okay, so the goal here is how to get my delta G negative if you want your reaction to go towards the product side. Under these two scenarios, okay, temperature plays a role. Okay, because in this scenario, it's delta H favored, but in this fourth scenario, it's delta S favored. Okay, so that's where temperature plays a role. You see in these first two conditions, both delta H and both delta S are favored. Okay, in this situation. In the second situation here, it's delta H disfavored and delta S disfavored. So if they're both disfavored, the reaction obviously is not going to be favored, it's going to be disfavored. Okay, so you see how these two communicate with one another to determine whether delta G is positive or negative. And under this scenario where one is favored and the other is disfavored, you have to look at temperature and its magnitude. All right, have a good weekend, everyone. I'll see you all in the lab if you're attending. If not, I'll see you on Monday.